Luc, you can go. Thank you very much.
Okay, thanks, Christophe. So we'll talk about some simulation of atomization process from DNS. DNS is an acronym for direct numerical simulation, and to industrial application. I got some. J'arrive pas à passer mon slide avec ça. Comment ça marche? Okay. So I will talking about multi-phase flows. So multi-phase flows are ubiquitous. You have, for example, films with liquid flowing down a wall, some atomization of conical liquid sheet or planar liquid sheet, which are a system of atomization in aircraft or rocket injection system. You have also interaction of droplets on wall. Here you have a picture of an experiment of high-speed droplets impacting on a solid wall. You have also formation of spray. When the liquid part is atomized, it will break up in small droplets and form a spray that will burn, for example, in combustion chamber of aircraft or rocket engines. And on this last picture, you have an experimental photograph of liquid oxygen jets sheared by hydrogen. This is the system of propulsion in rockets launcher. Okay, so the idea is to understand how we go from the bulk liquid phase to the atomized phase in order to provide industrial people a way to optimize the injection system of this type of engine. Okay, so it's really a multi-case flow ranging from for example, in this case you have injection system of a few millimeters to a droplet up to several microns, so you have 2 or 3 or 5 order of magnitude of size variation in this type of physical problem. Okay, so the idea we developed from years at ONERA is to have a clear understanding of the physical phenomenon. So to do that, we have experiment. So this is the name of some experiment we have. This is for aircraft engines. This is for rocket engine. But in such a phenomenon, it's often difficult to have accurate investigation tools to see how what's going on in the near zone of the injection system. So in order to get insight in the physics of such a phenomenon, we play with DNS code. The DNS code means direct numerical simulation codes. That is codes which are accurate enough with enough refining grids in order to catch all the scale of the problems without any needs to model. This is the dependent of experiments. This is, we call that a numerical experiment to get inside on generally some basics configuration, so academic configuration, which are more simple than the real problems, but which help us in order to get more insight and more understanding on what's going on. So we have two code to do that. This code digit which is incompressible one, with Cartesian grids and with interface tracking feature. Another one which is weakly compressible, which is unstructured grid, and based on the two fluid models, and which interface is captured by a diffuse method. So this is this second code is kind of prototype of the industrial code we developed from years at ONERA, which is called CEDRE, which is a general multi-purpose CFD codes based which can deal with reactive flows on general unstructured grid, like for example open forms. So in this code, it's a multiple solver code. You can plug in this a Navier-Stokes solver, a Navier-Stokes multi-fluid diffuse interface solver, a dispersed Lagrangian fast solver, and a dispersed Eulerian fast solver, a film solver, and other coupling like interaction with wall, with thermic model, and so on. But this is very general solver, but unlike this 2.1 is not is more rough, I can say, on the type of the result you can give, because it's generally based on RANS for Reynolds average Navier-Stokes equation, or LES approach for large estimation. So the idea is to use experiment and direct numerical simulation to improve modeling, which is developed in this code in order to simulate industrial problem like this 2.1. This is the mascot experiment simulation, which is a liquid oxygen jet surrounded by a co-flowing hydrogen jet at high velocity, and it is a two-phase reacting simulation. So I will go first to the DNS approach. I will mainly focus on the incompressible part of the digit code, which is a building block for a DNS code for assisted atomization. The code has been developed from around 12 years at ONERA. So the two phases are incompressible, and we simulate the interface by an interface tracking method. Okay, so we try to capture the interface between both gas and liquid phase. Here's material. We have developed some interesting feature like momentum conservation, consistency approach, and we also have some ingredient to treat to deal with complex geometry. So this is basically the equation we solved. This is incompressible Navier-Stokes equation writing conservative force, and here is a kind of function which is tagging the interface. We have mainly developed the tracking interface method based on the level set. So the level set is a function, a scalar function, which represents the signed distance to the interface. So this is an implicit representation of the interface. And we also treat the jump of quantities at each interface, like normal stress and tangential trace by a ghost fluid approach. We don't have any smearing of the jump condition at interface. We improve the mass conservation by coupling a level set with volume of fluid. Volume of fluid. Here you have a representation of a piecewise linear interface in this cell. So in blue you have the level set function which is characterizing the interface, and here the approximate volume of fluid piecewise linear reconstruction. And as volume of fluids are very accurate in mass conservation, we couple these two in order to get to improve the conservative property of the basic level set. So it's quite classical. We have also developed some adaptive Morphiman technique in order to gain in performance and memory and CPU time. And the idea is to refine the grid nearly in the neighborhood of the interface and unrefined in the zone when there is no interface. But in the problem of atomization, as the atomization will grow, you will produce a lot of droplets. So if you use adaptive mesh refinement, you will refine everywhere. So we have modified this in order to stop the refinement and also maintain the capture of the droplets. In fact, here you have an example of the algorithm we have developed. So here you can see a ligament in the refined zone, which is forming a droplet. This droplet is broken from the ligament. And so we detect this droplet, and then we transform the droplet in a kind of spherical particle, which is identified. And then we unrefine the mesh around this particle, and this particle is treated in a classical Lagrangian way. So with this, we gain in the refinement process. So we have something which more efficient than a full AMR. The main hypothesis assumption in that case is that these droplets will remain spherical. Okay, this drop doesn't undergo a secondary breakup. Here you have an example of such a simulation. So this is here you have the experiment. So this is top view of the experiment. So you have a liquid, a 2D liquid sheet, which is sheared by two co-flowing gas flow. So the velocity of the liquid is 2 meters per second, and the flow, the gas flow around 50 to 70 meters per second. So this is a snapshot of what is going on. So you see the formation of some wave at the surface of the liquid, and then you can see here secondary instability and the formation of kind of membrane, and these membranes are broken and are going burst to ligaments, and these ligaments which will atomize and form the final droplets here. So this is the experiment. This is a simulation. So you can see that we have really a very good qualitative agreement. And here you can see the methodology we use in this coupling AMR and Lagrangian droplet transport. All the colored droplets are when they are formed are followed by Lagrangian single Lagrangian method. So you have here a view of the PDF of the droplet diameter in comparison between the experiment and the simulation. So we can see that we catch mainly the same shape of the PDF. We have some difference in the value. We produce more droplet than experiment. Okay, but it's quite difficult also to really compare this type of things, because we have perhaps not quite long enough computational domain, so on. So, but well, we are quite happy with this type of comparison. So we have also improved this code in order to have what we call a consistent conservative momentum discretization. Because when you play with this type of simulation, we try to play with the actual density ratio. You have a density ratio between gas and air, gas and liquid about 1000. And we can have a high velocity up to 100 meters per second. So in the methodology, initial algorithm we use to discretize Navier-Stokes equation coupled with interface transport, we can have some we use, in fact, what we call a staggered mesh for the velocity compared to the level set and the volume of fluids. So we can have some inconsistency between the way we compute the velocity and the way we compute the density. And when the density ratio is high, this conduct to unrealistic velocity and the code blocked. So we have to write that. So we have developed a methodology to do that. I will not go for perhaps into detail of that. It's quite technical. So perhaps, roughly speaking, here you have an example of the grid. So this is a grid for the level set, the volume of fluid and pressure. This is a grid in red for the velocity. Horizontal velocities. This is a grid in blue, control unit for the vertical velocity. So we transport, in fact, two density. This is here for this velocity. You will have a y for this velocity in order to have the good density at the velocity location in order to get back the good momentum. Okay, so this is just a result. Here we transport in this simple test case high density droplets, which is 1 million heavier than the quietest gas around it. So this droplet is convected at constant velocity. So this is the old method. This is the new one. So you can see that when you have with this correction we have really an improvement. So you can see that the normalized kinetic energy evolving in that case is constant because this is a simulation without it's only inertial, without viscosity, without surface tension on an inviscid simulation. So we have to conserve energy, in that case kinetic energy, and so we can see that in that case it's a good correction. Okay. Some results. So it's the first one. It's to show you some result about some canonical experiment, which is the interaction of a liquid jet in a cross flow. Here you have a liquid jet coming from this hole, and here you have a cross flow which will impact this jet. So we have one of the characteristic number to identify the different regime in this type of simulation or experiment is the momentum flux ratio. It's a ratio of the liquid momentum over the gas momentum. So as you increase this flux, that means that there is more energy in the liquid part than in the gas one. So you have two snapshots of the simulation with the digit code, and here you have a comparison of experiment and the numerics. The experiment has already has been done also at ONERA by a colleague. So this is the shape of the mean shape of the liquid jet. So you can see we have quite a good agreement between the both. You can see also that we play with quite huge grid because, well, this is DNA simulation, so we have to simulate all the scale, even if for the liquid part we don't really know if we are resolved enough. Anyway, another example, it's a problem which is interesting us. It's a problem of droplet impact, liquid droplet impact at high velocity. So before we do that, we have checked that the code is able to simulate quite simple experiment at a very low velocity. So this is the experiment of Yokoi, and this is simulation. So we can see we have really a good agreement. Another experiment of Cosali, an Italian colleague, where here you have our numerical result, the experiment of Cosali, and another numerical result. So we can see again that we have a good behavior of the code. So here in this simulation, the idea was to check the influence of the remaining liquid film. So this is the thickness of the film in terms of microns. The droplet is about 300 microns. So this is tenths of the droplet diameter, and this is 5 micrometer and 1 micrometer. And you can see that as you decrease the thickness of the film, you modify really the way the droplet is splashing on the wall. So it's important. Well, the future application of such simulation is to understand the problem of icing when you have a high velocity droplet impacting on aircraft wings. As I told, we can also play with more complex geometry by developing some immersion interface methods that we plug solid in the computational domains in order to have geometry which are a little bit more complicated than only a square or cube or parallelepiped. So here we have tried to reproduce the experiment of the planned liquid sheet. This is a 2D simulation, and so you have the zoom of the liquid sheet, which is torn, and then he's shredding droplet in this zone. So we compare here the frequency, the main frequency, which is a primary atomization frequency, which is the frequency of the flapping of this liquid part. So here in green we have the experiment part as experiment results. In red, the 3D simulation without any immersive interface method, and here the 2D simulation with immersive interface method, and we can see that taking into account the geometry improve a lot the result, even if there is again some discrepancy between the experiment and the DNS. However, we have the good slope of the, and so it's better than that. Okay, so it is interesting to be able to deal with a little bit more complex geometry with immersive interface. Let me now go to the large scale approach. So this is mainly the algorithms that are coded in the CEDR platform, the CEDR solvers. So the objective is to be able to simulate very complex geometry, really a complete combustion chamber from the injection system up to the outlet of the chamber, and also to have not only round stimulation but unsteady simulation based on more or less large eddy simulation techniques with a multi-phase flow. Okay, so the idea is to treat this with a multi-phase and multi-species approach. And as the geometry can be very complex, and the grid is an unstructured general grid, so you can have polygonal cells and so on. So it's difficult to have an interface capturing approach. So we we jump to what we call a diffuse interface method. That is the liquid fraction, for example, is followed by solving a kind of transport equation like this, okay, which y high is mass fraction of one of the pieces or one of the phases. So this is quite simple to add more phases in this approach. Well, you have to play also with a thermodynamic property, which is not so simple, but well, from the transport equation is quite simple, and it can be extended naturally to multi-species, and it also a compressible one approach, so they can deal with high-speed injection system like in some rockets engines, supersonic ramjet or something like that. Well, some drawback of this approach is you could have problem with when you have strong velocity or temperature gradients at the interface, and when you are in zone where like in combustion of like with hydrogen and oxygen, so liquid oxygen and hydrogen, so you can have a huge temperature gradient, so it's not so simple to play with that. Here you have an example on well, academic relative problem. So you compare level set approach, the approach I told you before, and the multi-fluid solution. So you can see you smear a little bit the interface. Okay, so you don't have a clearly line which is delimiting both phases. You have a zone which is dependent of the thickness of the grid, of the resolution of the grid. But anyway, you can get the good shape if you have quite enough resolution with this approach. So this is an example to show the complexity of the systems. This is a really an injector, TLC an injector, and the TLC burner. TLC was a European grants with people from England, Germany, and so on, France and Italy, a big grants to improve tools for aeronautics companies for the simulation of internal flow in combustion chamber. So here you have the injection system, and here you have the flames, and in that case, to put the liquid phase, the kerosene, so we have only put droplets with some distribution of density, of velocity, diameter, and temperature, and track them by a Lagrangian way, and then evaporate them and burn them. Okay. What we want to do now is to really simulate what's going on inside the injector by this diffuse interface approach, and then the methodology must be able to break the bulk phase in droplets with a good diameter, and then go on with the other problem of vaporization and combustion. So the idea is to have in the same code a methodology will be able to treat from this continuous bulk phase up to the fully dispersed phase. Okay. So the idea is to split in different zones. So the zone near the injection system, which will be quite, which will have quite high resolution, to be able to capture at least the flapping, so the main primary instability, which then give birth to the formation of ligament and breakup by this multi-fluid diffuse interface approach. Then when when you go downwind of this zone, and you will unrefine the grid thanks to unstructured grids, which is quite simple to change the resolution of the grid. And in this zone, this multi-fluid interface approach will be not able to capture all the subgrid droplets. So for the moment, we can detect by some criteria the zone where we are in this unresolved zone, and transform the liquid friction, the diffuse liquid friction, in droplets where we impose the size and the velocity. Okay, but it's for the moment we have implemented this methodology to do that, but the code is not able to define by itself what is the size of the droplets and the velocity and so on. And the idea is to improve that by defining some kind of subgrid droplet generation model, like you do when you play with a single-phase LDS approach, in order that depending on the flow field, on the topology of the liquid phase, the value of the volume fraction or mass fraction of the liquid, that the code will by itself, by a model, be able to impose by itself the good size. And then we coupled, because the solver CEDR is multi-solver, we can couple the dispersified inside the Lagrangian or Eulerian dispersified solver. Okay. So this is, roughly speaking, the methodology we try to develop to do all this stuff. And to do this modeling, we use experiment data when we can, and also DNS result by analysis on canonical academic configuration, some the phenomenology of the flow, and try to extract from the DNS some characteristic parameters or characteristic behavior, some similar behavior we can that can be used to develop the model. Here you have an example of this approach for the moment. So here we use the code CEDR to simulate this upscale injectors, which is a pressure injector. So you can see the four liquid entrants. So this is in rotation. Okay. So the liquid bulk phase rotate. So you can see this here. And then when you arrive in this zone where the grid is less refined than this one, so you will diffuse what is called the volume fraction, and then produce droplet. In that case, we impose the size of the droplet. Okay, only to this picture show you that the methodology for going from the bulk phase to the dispersified solver is working. Okay, now we are to work in order that a model must be able to give, depending on the physical condition in this zone, the good droplets distribution, or at least a mean droplet distribution, which is not so far than the actual droplet distribution. So this is another example for the liquid jetting cross flow. Again, okay. So this is a comparison we have done at ONERA between experiment and numerics using this methodology with the code CEDR. So with the multi-fluid liquid approach, the multi-fluid model is what we call a four-equation model for air and water phase with surface tension, which is used in the zone. Then in this zone, we use a Lagrangian dispersive phase solver with atomization model for secondary breakup. And we inject the particle when at the zone, depending on the value of the diffuse mass or volume fraction, but we fixed the diameter of the particle. And we also coupled this because in experiment we have the wall at the same size. As the jet can penetrate quite high in the bench, you can have formation of the or a film. So we have also a film solver. So we couple all these three models for the configuration. It is an unsteady configuration. So you can see here the bulk phase, then here the droplet, and here on orange from light orange to dark orange, you can see the formation of the film. Okay. So this is a snapshot of instantaneous picture of the simulation. We have done also some comparison because in this case we play with some kind of acoustic interaction with two-phase flow, which is used to understand what we call combustion instability, which are generally driven by some acoustic coupling between liquid gas and the structure of the burner. Here we compare the simulation and the experience, so we can see that we have a good agreement, and also some droplet phase delay at a certain point. Here again, we can see that we have a quite good agreement with the simulation. But again, in this case, we impose the size of the droplets. Okay, so our next work now is to really work in order to try to input a new LES-like model for this liquid gas interaction. Well, this is well also some numerical results, and we go now to the modeling part. So this is actually a work which is in progress, really. So we have one thesis which is ending at the end of this year on that. Though, as I already said, we need some subgrid information, topological, when transitioning between scales. So between this large scale, which are enough result, up to the small case. Okay. The idea is to use what it is called the surface density approach, which is a approach which has been developed by Roland Borghi and his teams years ago in the framework of simulation of launcher in the 90s. And in fact, this quantity is represented the density of surface of the liquid, and liquid gas interfacing. Okay. The idea is to use this type of convection, diffusion, and Chern equation, and the main part of the modeling part, which focus on this term, which is a source or sink terms. And in order to give to the model by extracting information for DNAs, how to give a good representation of this term. Okay. So some works in the world is also done on this in Rouen, in France, at Coria, with the team of Le Baye-Chenel. They find that the search terms can be linked to the characteristic time and critical surface density. Okay. So our idea is to use a simplified simulation to better understand this fact and to try to give something which a little bit more elaborate than the model of Le Baye-Chenel. In order to do that, we have to develop an appropriate DNS analysis tool, because we have to capture and to see, to follow during the simulation the production of the surface density, and tracking all the type of structure from ligament to blobs to droplets that are formed during atomization process. So we have begun by doing some 3D DNS simulation of periodic liquid shear sheet. So here you have we have made some parametrical study. M is a momentum flux ratio, and we try to understand how the surface density is evolving during time. So you can see that while the three curves are the same shape, but they are not superposed one over the other, so they are not collapsed. So we try to understand if we can find some time scaling in order to make these curves to collapse and to extract some characteristic, global characteristic time or scale, which can be used in order to improve the system of the density interface equation. So by doing some non-dimensional times, we can see that all the curve seems to collapse, and we have the maximum production of surface density at the same times. And we, roughly speaking, have the same, at least in this part, the same slope for the surface density, the non-dimensional surface density. Well, this is again the same to show you here the same non-dimensional time. We also try to analyze really the population of the different structures that are formed during atomization from ligaments. So we have developed a tracking algorithm which can be used to analyze both the shape of the structure and also the velocity, and also can be used to tag both in space and times I can explain. Well, if I pick a droplet at certain times, at a certain position in the numerical domain, I can go back to say this droplet has been came from this ligament at this time, and so on. So we can have really an history of the liquid atomization. So it's interesting in order to classify all the structure depending on the parameter like the momentum flux ratio and so on. So really it's a very hot thing that I present to you, because we are actually work on that. So all the things are not so clear for us. So it's really the work we are playing now. Here you can see in blue both the spherical, roughly speaking, the spherical part of the droplets and the non-spherical part, which can be other blobs or ligament. Okay, so you can see during time how this quantities is evolving during the simulation. So the first things we have done was with periodic simulation, which are not so realistic compared to real problems. So we at the time are doing the same with really spatial simulation. So and try to see in the same configurations that I've presented before, the shape inject on liquid sheet atomization. So this is the same configuration. So with immersion interface, I only plot here the shape of the liquid part. So you can see depending on the time, so the topology of the liquid atomization with primary instability, formation of membrana which are broken, and then ligament, and then here ligament which are broken into droplets, and which some small drops up to quite important drops. Okay, so we are working on the analysis of all this parametrical simulation we have done in order to understand how we can extract from them some relevant scales, both temporal scales and spatial scale, in order to build a simple, at first, terms for the sink or source term of the density surface transport. So I will end my presentation here. So what can be said is that, well, this type of DNS is really an interesting tools to have an understanding on this complex process, because as you can see, when you see this, you can't really, with experiment, try to give the liquid distribution of droplets, the size of ligament. It's very difficult. You can have some mean quantities, measurement, frequency here. We can measure frequency here, but you can. It's very difficult to have detailed information on the size of the drops, the velocity of the drop, the history of the drop formation. In the simulation, by our tracking technique, you can say this, for example, these droplets come from this ligament, this come from this, and so on. So we have a fully Lagrangian tracking which can help us to really rebuild the story of the atomization. Okay, and the idea is to put all the information we can gain from DNS in the large-scale simulation. Okay, I will stop my presentation here. Thank you.